Hello lovely kittens, these are your key concepts in chemistry, my favourite topic, and this you have to know really well if you want to be successful in all the rest of your chemistry. The model of the atom has changed quite a lot over time. You don't need to know all the details of this, you need to know that Rutherford was responsible for discovering the nucleus and protons. That Chadwick discovered neutrons. And that Bohr is our current, or developed our current model. Here we have the structure of an atom. We have electrons that are on the shells around the outside, protons that are in the middle, and neutrons that are in the middle. And this bit in the middle here is collectively called the nucleus. Protons are in the nucleus. They have a mass of 1 and a charge of +1. Neutrons are also in the nucleus. They have a mass of 1 and a charge of 0. Electrons are in the outer shells. Their mass is 1/2000 and they have a charge of -1. On the periodic table you will see lots of boxes like this. This tells you all about the elements. This is the element's name, the symbol, and there are two numbers. This is the atomic number, and this one is the mass number. Now for these, location doesn't matter. Different textbooks, different sheets are going to put them in different locations. The larger one is the mass number, and the smaller one is the atomic number. The atomic number tells us the number of protons and the number of electrons in an atom. The mass number is the number of protons plus the number of neutrons. So here we have calcium. The smaller number is the atomic number, the large number is the mass number. And if you want to find the number of protons, it is simply the atomic number, so in this case 20. The number of electrons is also the atomic number, so again 20. The neutrons is the mass number, which is 40, minus the atomic number, which is 20, equaling 20. Here we have two different isotopes of carbon. Carbon-12 and carbon-14. Working out the number of protons is exactly the same. It's the atomic number, so for both of those that is 6. The number of electrons in an atom is the same as the number of protons, so that is 6. But the neutrons here is different, because for carbon-12 it is 12 minus 6, giving us 6 neutrons. And for carbon-14 it is 14 minus 6. Giving us 8 neutrons. So an isotope is something that has the same number of protons but a different number of neutrons. And a proton is what identifies the identity of an atom. You may have noticed from the periodic table that some things have 0.5 mass, so chlorine has 35.5 mass, which is frankly ridiculous because we can't have half protons or half neutrons. This is because the mass is the relative abundance of all the isotopes. There are two main isotopes of chlorine, chlorine-35 and chlorine-37. 75% of naturally occurring isotopes are chlorine-35 and 25% of the naturally occurring isotopes are chlorine-37. To work out the mass, this is what we do. You take the MR, 37, times it by the relative abundance, 25%. Do this for all of them. 35 times 75 and then divide that by 100. 37 times 25 is 925, plus 35 times 75, that's 2,625 over 100, giving us 3,550 over 100, making it 35.5. Here we have our wonderful, beautiful periodic table. It is a list of all the elements which are known to exist. Elements are a single type of atom. An atom is a very, very small thing. The word atom is actually Greek for uncuttable. And when they named them, they thought it was the smallest thing possible. The periodic table tells us loads and loads and loads of information about the elements, the range of elements that are known to exist. There are still loads yet to be discovered. A compound is two or more elements that are chemically bonded together. That's the important thing. Chemically bonded together. Our periodic table hasn't always looked like this. The first attempt at a periodic table was by Newlands in the 1800s. He tried to group things into octaves and rate them by pattern, which is a really good idea, except we have oxygen and iron in the same group, and they have very different properties. He arranged them by mass, but he didn't leave any gaps, and he tried to force things in to have similar patterns or properties as other things, and it didn't really work. Mendeleev was the next person to have a go. He also arranged things by mass, but the key thing is that he left gaps in his periodic table, and because he arranged things so that they were in groups with similar patterns, and he left gaps, he could predict the properties of elements that have yet to be discovered, and he was correct in his predictions. A few years after he developed his periodic table, a couple of new elements were discovered, and they fitted in really, really neatly, really nicely to his periodic table. So this week's table was accepted. It has changed ever so slightly by then. We now arrange things by electronic arrangement, but that's a very, very subtle difference. The periodic table gives us loads and loads of information. The first bit of information it gives us are about groups. Now groups go down the periodic table. Group 1, group 2, 3, 4, 5, 6, 7, 8 or group 0. Groups tell us the number of electrons on the outer shell. So things in group 1 are going to have 1 electron in the outer shell. Things in group 2 are going to have 2 electrons in the outer shell. Group 6, 6 electrons in the outer shell. Group 7, 7 electrons in the outer shell. Periods go across the periodic table. So here is our first period, the one that everyone always forgets because it's only got hydrogen and helium in. Here is our second period. Here is our third period, and the periods relate to the number of shells that things have. They also remind us how many electrons there are in each shell. So in the first period there are 2 elements, which means there are going to be 2 electrons in that shell. In the second period there are 1, 2, 3, 4, 5, 6, 7, 8 elements, which means there are going to be 8 electrons in that shell. And we can use this information to tell us about the electronic configuration. Here we have magnesium. Here is magnesium on the periodic table, and we can see that the number of electrons it has is 12. It is in group 2 and it is in period 3. So that tells us it has 12 electrons in total. It has 2 electrons on the outer shell because it's in group number 2, and it has 3 shells because it is in period number 3. So when we want to draw the electronic configuration of magnesium, we know it's in period 3, it's going to have 3 shells. The first thing we can do is draw 3 shells. 2, 1, 2 go on the first shell. 1, 2, 3, 4, 5, 6, 7, 8 go on the second shell. That's the most that can fit in that shell. That brings us up to 10, 10, 11, 12, 2 electrons on the outer shell. From the periods, we know that the first shell can hold a maximum of 2 electrons, the second shell can hold a maximum of 8 electrons, the third shell can hold a maximum of 8 electrons, and then you only need to know up to calcium, so another 2 for your GCSE. Metals are going to lose electrons, and when we lose electrons we get positive charges, and non-metals are going to be gaining electrons, and when we gain electrons we get negative charges. Things in group 1 are going to lose 1 electron, so are going to be +1 ions. Things in group 2 are going to lose 2 electrons, so are going to be +2 ions. Things in group 6 here are going to gain 2 electrons, so are going to be -2 ions, and things in group 7 are going to gain 1 electron, so are going to be -1 ions. Ionic bonding is the transfer of electrons from a metal, which is on this side of the periodic table, to a non-metal on this side of the periodic table. Anything that is in group 1 is going to form a +1 ion, group 2 a +2 ion, group 6 a -2 ion, group 7 a -1 ion. Here we're going to make magnesium oxide. Magnesium is in group 2, so it has 2 electrons in its outer shell. Oxygen is in group 6, so it has 6 electrons on its outer shell. In ionic bonding, oxygen is going to keep the electrons that it's already had, and the electrons that were with magnesium are going to be transferred to oxygen. We call these dot and cross diagrams because one element has a dot for electrons and the other element has a cross for electrons. We then draw square brackets around these and indicate the charge. So magnesium has lost 2 electrons, so it's going to have a +2 charge. Oxygen has gained 2 electrons, so it's going to have a -2 charge. Here we have sodium, and it has an atomic number of 11, which means it's going to have 11 protons in the nucleus, and protons have a positive charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now in the atom it has 11 electrons drawn on here. Electrons have a negative charge. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now in an atom the positive charges and the negative charges cancel each other out, so the overall charge on the atom is going to be 0. However, when sodium makes an ion, this electron here goes away. So it still has the same number of protons. It's still sodium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But it's lost an electron. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has one more proton than it has an electron, meaning this is going to have an overall positive charge. Here we have sodium chloride. Sodium are the grey bits you can see, and chlorine are the green bits you can see. The blue lines are the electrostatic interactions, the electrostatic attractions. Because the way we get you to draw ionic bonding is really false. It's not just one sodium combining with one chlorine. It is this massive, massive, massive lattice of sodiums and chlorines, or whatever we're looking at, bonding with everything else. So one sodium here isn't just going to be bonding with the chlorine next to it, or the chlorine that it's exchanged electrons to. It's going to be bonded with all of the other ones above it, next to it, behind it, in front of it, everything that it can reach. So this ionic bonding is a massive, massive, massive network, not just the small things that we get you to draw in class. So for ionic compounds, the structure is a giant ionic lattice. Properties: it is going to have a high melting point, high boiling point, and it is only going to conduct when molten or dissolved. This is because the ions need to be free to move. Covalent bonding is the sharing of electrons between two non-metals, these up here. And these are the common ones you need to know how to draw. For each of these, you need to be able to give the name, the formula, be able to draw it with lines, and be able to draw the dot and cross diagram. So hydrochloric acid or hydrogen chloride, one element of hydrogen, one element of chlorine. Ammonia, NH3, nitrogen in the middle, 3 hydrogens coming off around the side. Methane, CH4, carbon in the middle, 4 hydrogens branching off it. Hydrogen, H2, very simple one there. Chlorine, halogens go around as diatomic molecules. Oxygen, we're getting a bit tricky now, has a double bond. Each line is equal to a pair of electrons. Here we have 2 lines, that is 2 pairs of electrons. We need 4 electrons being shared in the middle. And nitrogen has a triple bond, 2, 4, 6 electrons being shared in the middle. If in the exam they give you a picture and ask you to link the formula of it, you simply need to list what we have. So in the first one we have carbon and we have hydrogen, and then we need to count them. 1, 2, 3, 4, 5. Carbon, 5. Hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Last one, carbon, hydrogen, oxygen. We have 1, 2, 3 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens and 1 oxygen, so we don't need to put a number after that. It's really important that you write things in the right size and in the right place. So that is incorrect because your numbers are too big. That is incorrect because your numbers are in the wrong place. I seriously recommend you learn at least these formula. Carbon dioxide is CO2, water, H2O, oxygen gas, O2, hydrogen gas, H2, nitrogen gas, N2, ammonia, NH3, hydrochloric acid, HCl, sulfuric acid is H2SO4. For simple covalent compounds, such as water, carbon dioxide, oxygen, nitrogen, hydrogen gas, hydrochloric acid, or methane, oxygen gas, or water, as we have here, they are very, very small structures. They have covalent bonding. Their properties is that they have low melting points and boiling points. They're generally going to be a gas at room temperature or a liquid at room temperature. They do not conduct electricity. For giant covalent compounds, ones made of carbon, such as graphite, diamond, or any fullerenes, or silicon dioxide, they are going to have a giant covalent structure. Their properties are high melting and boiling points, and they do not conduct, and they do not dissolve. Here we have diamond. It is a giant covalent compound, or a giant covalent lattice. It is made of carbon, pure carbon, nothing else in there, and each carbon makes 4 bonds. So in the video you can see that the carbon is the black bits, the covalent bonds are the red bits, and each carbon is bonded to 4 other carbons. Obviously the ones on the edge aren't bonded to anything, but if you try and look in the middle you can see that they are bonded to 4 other things. The properties of diamond that make it really useful is that it's incredibly hard. It's very rare, it's hard to find, it's also very beautiful, which makes it very precious. But the main thing is that it's incredibly hard, so we can use it in drills. Graphite is also a giant covalent compound. It is like diamond, pure carbon, but each carbon makes 3 bonds to other carbons, not 4 like in diamond. The properties are that it is soft and it conducts electricity. Because it is in sheets, and there is a spare electron floating around in between these, that means it will conduct electricity. Graphite is what you find in pencils. Graphene is just a single sheet. If we were to compare diamond and graphite, they are both made of pure carbon. Graphite is made of 3 carbon-carbon bonds, diamond is made of 4 carbon-carbon bonds. Graphite is soft, diamond is hard. Fullerenes are either carbon nanotubules or Buckminster fullerenes, which are balls. These are again all made of pure carbon. They make 3 carbon-carbon bonds, but unlike graphite, which is soft, these are incredibly hard. Buckminster fullerene can be used as a lubricant in things that need lubricating, like electrical cycles or some parts of machines. It can be used for reinforcement, so where you need a very, very strong, very, very light things like aircrafts or bicycles. They can also both be used, or in the future be used, for drug delivery. And fullerenes, carbon nanotubules, Buckminster fullerenes, there are loads and loads of potentials for these, but they haven't been realised yet. With polymers, whether they have cross-links or not, are going to determine what their properties are going to be like. So polymers that do have cross-links are very, very fixed in place. These are going to burn upon heating, whereas polymers without cross-links are going to melt upon heating, because these polymers can slide across each other, whereas these ones cannot slide across each other. Metals are made up of positive atoms in a sea of delocalized electrons, and these electrons being free to move is the reason that metal can conduct electricity, and why it's so good at conducting heat. An alloy looks slightly different to a metal. We still have our positive ions, we still have our delocalized electrons, but there's something else in there as well. This may be another metal it's alloyed with, or it may be something else like carbon that it's alloyed with. Pure metals have layers. Layers can slide across each other. Because they have layers and because they can slide across each other, they are soft. Alloys don't have layers, or they have distorted layers. And the distorted layers cannot slide. And because the distorted layers cannot slide, it means they are hard. You need to remember all of the equations, remember the ions, and be able to work out what is going to come from a reaction. So if we have an acid and a metal, we are going to get a salt plus hydrogen. Acid metal oxide is going to give us a salt plus water. Acid metal hydroxide is going to be a salt plus water. Acid metal base, salt plus water. Acid plus metal carbonate is going to give us a salt, water, and carbon dioxide. To work out the formula of the salts, you need to know the formula of all of your ions. I've made flashcards to help you with this. You can watch the video. I'm afraid you're going to need to watch it over and over again so that you learn it. And then you're going to need to make sure that you combine the ions in such a way that they are neutral overall. The new style exams means there are a lot of wordy questions that incorporate a lot of skills all at once. In this question, you need to first of all recall the formula for things, then balance the equation. So hydrochloric acid is HCl, magnesium is Mg. Now we need to work out the products and the formula of the salts. A metal plus an acid is going to give us salts plus hydrogen. Hydrogen's the easy bit. It is H and then 2 because it goes around as a diatomic molecule. The salt is going to be magnesium chloride, but we need to know that magnesium is a 2+ ion and chlorine is a 1- ion. So it needs to be MgCl2 so that there are 2 negative ions for each positive ion. Now this is brought in a lot of skills, recall of the formulas, working out the salts, the products, so working out what type of equation it is, and then after all of that we need to balance it. So to balance our equation we draw a line down the middle, list what we have, hydrogen, chlorine, magnesium, hydrogen, chlorine, magnesium. It is really going to help you if you keep things in the same order. Circle the compounds that we have. List the numbers of things. So we have 1 hydrogen, 1 chlorine, 1 magnesium, 2 hydrogens, 2 chlorines, 1 magnesium. So you can see straight away we need some more hydrogens and some more chlorines. The easiest way for us to do that is to add another HCl on there. Then redoing our numbers, we have 2 hydrogens and 2 chlorines. That is balanced. Writing it out neatly for the examiners, because just leaving it like this won't get you the marks. We have 2 bubbles of hydrochloric acid plus magnesium turns into magnesium chloride plus hydrogen. You need to be able to take a set of words and turn it into a balanced symbol equation. So there is quite a lot for you to do here because you need to remember the chemical symbols for quite a large number of things. Water is H2O. That turns into hydrogen gas, which is going to be H2, plus oxygen gas, which is going to be O2. And now we need to balance it. Draw a line down the middle, circle everything, and list what we have. We have hydrogen, we have oxygen, we have hydrogen, we have oxygen. Count the number of things. 2 hydrogens, 1 oxygen, 2 hydrogens, 2 oxygens, sorry. So we need to increase the number of oxygens on this side because you see there aren't enough. Then we have to add another H2O, put that in a circle, redo our numbers. We now have 4 hydrogens and 2 oxygens. So our oxygens are balanced, but now our hydrogens we have more on this side than we do on this side, so we need to add more hydrogens here. Again, the only thing we can do is to add a whole another bubble. We now have 2 hydrogens here, 2 hydrogens here, making 4 in total and 2 oxygens. So now we have 4 hydrogens on this side, 2 oxygens, 4 hydrogens and 2 oxygens. We need to rewrite that neatly for the examiner, so we have 2 bubbles of H2O turning into 2 bubbles of H2 plus 1 of O2. When you are working out the MR, which is the relative formula mass, you need to take all of the ARs, which is the relative atomic masses, and add them together. Now the mass, remember, is the larger number of the two. Doesn't matter where it's located, it is the larger number of the two. So hydrogen has a mass of 1 and we have 2 of them. Sulfur has a mass of 32. Oxygen has a mass of 16 and we have 4 oxygens. So 1 times 2 is 2 plus 32 plus 16 times 4, which is 64. Add those together, we get 98. The empirical formula is the lowest ratio of all of the elements in a compound, and this is how we work it out. We have a compound that is 75% carbon and 25% hydrogen. So we're going to list carbon, hydrogen, write down the number in the question, and units do not matter for this. Not very often that I say that, I'm only lagging utilitarian units, but whether it's percentage, whether it's tons, whether it's grams, units do not matter. Write down the mass from the periodic table. So carbon has a mass of 12, hydrogen has a mass of 1. You then need to divide the number in the question by the mass. So 75 divided by 12 is 6.25. 25 divided by 1 is 25. You then need to divide both of these by the smallest number. 625 is smaller than 25, so we need to divide both of these by 625. 6.25 divided by 6.25 gives us 1. 25 divided by 6.25 gives us 4, meaning there is 1 carbon to every 4 hydrogens, and that is the empirical formula. There is loads and loads of maths in this. The majority of the content of this topic and a few other bits that come out elsewhere. You can get loads and loads of practice for this in my book, Maths, the chemistry bits. It has 60 equations for you to practice balancing, loads of titration calculations, loads of bond density calculations which come up later in the course. Lots and lots of things for you to do. A mole is not a rather cute blind black furry thing, but it is the unit for the amount of a substance, and that is going to be 6 times 10 to the 23 atoms, ions, or molecules. And that is because that is the number of carbon atoms in 12 grams of carbon. So our equation for this is going to be moles is equal to mass over mR. This is an incredibly complicated question which combines a lot of skills. First of all, you have to work out the formula of things, work out the equation, balance the equation, and then finally work out the amount of hydrogen peroxide. We have hydrogen peroxide decomposing into water, H2O, and oxygen gas. Now we need to balance the equation. Hydrogen, oxygen, hydrogen, oxygen, 2 hydrogens, 2 oxygens, 2 hydrogens, 3 oxygens. So we can increase that by putting more oxygens over this side, H2O2, giving us 4 hydrogens, 4 oxygens. Now we need some more hydrogens and oxygens over the right hand side, pop another H2O on there, and we have 4 oxygens and 4 hydrogens, giving us a final balanced equation of 2 hydrogen peroxides making 2 water and 1 oxygen. Now we need to know how much oxygen gas is given off from 40.8 grams of hydrogen peroxide. The first thing we do is to work out the masses involved in the equation. Hydrogen has a mass of 1 and there are 2 of them. Oxygen has a mass of 16 and there are 2 of them. That is 2 plus 32, giving us 34. And because there are 2 of them, that gives us a total of 68. Hydrogen is 2. 1 times 2 equals 2. Oxygen is 16. 2 plus 16 gives us 18. 18 times 2 gives us 36. And then oxygen is 16 times 2, giving us 32. So we can say that if we had 68 grams of hydrogen peroxide, it would decompose into 32 grams of oxygen. But we don't have 68 grams of hydrogen peroxide. We have 40.8 grams of hydrogen peroxide, and we need to find how much oxygen that decomposes to. This is now just a ratios question from maths. I'm going to put a 1 in there. To go from 68 to 1, we need to divide by 68. So that's what I need to do on the other side as well, divide by 68, giving us 0.47. To go from 1 to 40.8, we need to times it by 40.8, which is exactly what we need to do over this side, times 40.8, but I don't want you to clear your calculator. I want you to keep the number in your calculator. So 0.47, or the long number in a calculator, times 40.8 gives us 19.2 grams. If you had cleared your calculator and got just did 0.47 times 40.8, you would have got an answer of 19.176, which is close but not the same answer. What you've introduced is a rounding error. When we are working out concentration, that is going to be your amount divided by your volume. Concentration is measured in moles per decimeter cubed, amount is in moles, and your volume is in decimeter cubed. When you have an equation, there's always going to be a limiting reactant, and your reaction is going to continue using up the limiting reactant, forming product, until you get to the point where your limiting reactant is used up. And at that point, the reaction is going to stop. So whatever you don't want your limiting reactant to be, you always need to make sure the other one is in excess.